Okay, so I think we'll get started and then hopefully others will join us as the session progresses. So good morning and good afternoon, everyone. Today, welcome to Module 8 of the Vital Statistics course. And this week we'll be covering life expectancy and life tables. So I'll be starting today's session with a brief overview of the history and reason for life tables. And then I'll be handing over to my colleague Petra from UNESCAP to continue on the methodology and calculation of life tables. So why do we construct life tables? Well, life tables are one of the most essential tools in the demographer's toolbox, and they are used in the analysis of mortality and to estimate life expectancy, which is an important indicator of the overall health of a population. However, life tables may also be used in other contexts for any type of survival analysis, as well as mortality analysis. And one example of this may be the age of onset of chronic disease, where the outcome of interest would be the diagnosis of disease instead of mortality. So this means that life tables are really useful for including data which may otherwise be lost to censoring or also lost to follow-up. So what is a life table? It basically summarizes a cohort's experience of mortality, and it can be used to trace a cohort of newborn babies throughout their life, showing for a person at each age the probability that they will die before their next birthday. So from this starting point, a number of statistics can be derived, and thus also included in the table. So this includes the probability of surviving any particular year of age, the remaining years someone can expect to live once they have reached a certain age, the proportion of the original birth cohort still alive, and one of the most important indicators which you'll see calculated from life tables is life expectancy. We also calculate life tables separately for males and females because of their different mortality patterns. Now we have two types of life table which we can calculate. We have cohort and period life tables, and I'll just cover now what the difference is between those two types of life table. So cohort life tables show the probability of a person from a given cohort dying at each age over the course of their lifetime. So when we talk about cohorts, we are generally talking about a population that are all born in the same year. For example, all males born in 1900. The cohort life table uses age-specific probabilities of death, which Lauren covered in her previous modules on mortality analysis. And these mortality rates in cohort life tables are estimated using observed death data from the cohort. So cohort life tables use a combination of observed mortality rates for past years and also projections about mortality rates for past years and projections for mortality rates for the cohort in future years in the case that they haven't all yet died. Cohort estimates of life expectancy are regarded as one of the most accurate measures of how long a person of a given age would be expected to live. Especially compared to period life expectancy, which provides more of a cross-sectional view of mortality at one point in time. So one of the main problems of constructing cohort life tables is that we need to wait for everyone to die. For example, if we're looking at a cohort of all females born in 2000, we'll need to wait, for example, 85 years since 2000 until many of those people have died. So because if we were to look at it now, people born in 2000 are only age 21. So in that case, we would have to use projections. So to do this, we can create a synthetic cohort or apply the prevailing period age-specific mortality rates to this hypothetical cohort of newborn babies so that we can predict mortality and life expectancy in the future. Which brings us on to the other type of life table, which is period life tables. And these tend to use current mortality rates from a single year or group of years, and they assume that those rates apply throughout the remainder of a person's life. So in this sense, it provides a cross-sectional view of, excuse me, of mortality and survival experience, which means that any future changes to mortality rates are not taken into account as we don't have that information yet. So it is what is otherwise known as a synthetic or hypothetical cohort based on the mortality experience of a hypothetical cohort of newborn babies who are subject to the same age-specific mortality rates on which the table is based. And the age groupings usually used in life tables may also vary depending on the size of the population, but usually 5-year age groups are used. But for smaller populations, for example, countries in the Pacific, you may use 10-year age groups. So we have three main assumptions when calculating period life tables. And the first is that it uses a hypothetical closed population. So it does not consider migration in or out of a population. Secondly, they assume that people experience homogeneous or the same risks across age and time, which may not actually be the case, especially in older age groups. And the third assumption is that there is no measurement of change over time, as we know that over time, survival within a population may gradually increase as people in general are living longer, healthier lives. So just a brief history of life tables. Life tables do have quite a fascinating history and have been used for centuries to estimate and predict mortality. They were first established in the 17th century and were known as the bills of mortality, and the information obtained, it used the information obtained from christening and deaths lists in London. So as I mentioned earlier, life tables also have different purposes, and this slide just provides a little overview of those other applications of life tables. So we have single decrement, and this is the most common type and probably the one that you will use the most often. And this measures moving from one state to another. In this case, it measures from the state from being alive to being dead. Then we have multiple decrement, which is the one on the bottom left of the screen. And this is where you may be interested in estimating being alive and then death, but you want to look at what was the cause of death. And then we also have multi-state or increment decrement, where populations may transition into different states throughout the life course. So for example, if we take marital status, where one may transition from being single to being married to divorced, widowed, or even death. So life tables have lots of applications to assess daily phenomena occurring throughout a life course. You may also see life tables being referred to as either abridged or unabridged, and this just describes whether age groupings have been used. So unabridged is when single years of life are used, and you may see this also being described as complete life tables. And abridged is when we use 5-year cohorts, or perhaps other cohorts such as 10-year cohorts, depending on the size of the population. And here we've just provided an example so that you can see visually what the difference is between complete or abridged or unabridged or abridged life tables. So On the left here, we have a complete life table. So you can see in the left-hand column, we have single years of age. And on the right, we have an abridged life table, which uses age groups based on the assumption that death rates are similar at neighboring ages. And just to note also here that usually in most abridged life tables, we calculate mortality separately for the age groups 0 to 1 years and 1 to 4 years. And this is because mortality during these ages is very different to mortality at later years. Its mortality, especially in the first year of life, is much higher. So we calculate these separately. And then before I hand over to Petra, I just wanted to provide a quick reminder of the differences between rates and risk, which is something that is important to bear in mind when estimating life tables. And rates and risk are often confused, and it's made more difficult by the popular description of both things as rates. For instance, infant mortality is a risk and not a true rate, but the terminology of this is unlikely to change. So you'll see here as well on the right-hand side of the screen equations which show you the differences between probabilities and rates. And a true rate, as you'll see here at the bottom equation, has a denominator of the average population across the interval concerned, or otherwise known as the person years of exposure. The denominator is also often described as a midterm population, and this may be the origin of the term central rate. And the risk, which is also known as a probability, and this is the proportion of subjects affected by the event under study between the beginning and the end of the interval. Therefore, as you'll see here, the numerator will be, for example, the number of subjects at the start of the interval, or the number of people experiencing an event. And then the denominator is the total number of outcomes, or the total population. And it's also important to note that a probability can never be greater than 1. And under certain circumstances, rates can exceed 1. So with that, I'm now going to pass over to my colleague Petra, who will take you through the methodologies of life tables.
Thanks, Chloe. Maybe I can share my screen?
Sure, I'll stop sharing.
Maybe, are there any questions up to now? Is everything clear?
Sorry, Petra, I'm trying to stop sharing my screen. I think if you click share, it should just override my...
I will do that right now.
Edit? Okay.
Okay. So thank you for that, Chloe, and I'll move on to the life table notation. The thing about the life tables is that conceptually there's nothing particularly difficult, but it does get a bit confusing. So we're going to go very carefully through the notations just to make sure that it's completely clear, because this is used throughout write formulae or refer to different columns in the life table. There's often a subscript which appears before the symbol, and this is going to define the width of the interval. So because we're using mostly abridged life tables, it's really important to know how many years there are in the interval, whether it's 1, whether it's 5, or whether it's 10. The subscript after the symbol, that defines the starting point of the interval. So whatever age we're starting that interval. If there's no left subscript, then it's not referring to an interval, but it's referring to an exact age. So if you see X, that's the exact age, for example, 40, and then N, which is commonly used, that's referring to the width of the interval, and that will be something like 1, 5, or 10. Now, we're going to focus in this course on the single decrement life table, just moving from alive to dead. That's the only two states which are possible. And obviously, you can't go the other way in this case. So we'll be looking at the different columns in the life table. And what I'm going to do now is I'm going to go through the different columns, and we're going to look at them conceptually. And then we'll look more closely at the formulae for actually counting the columns. And please do stop me if there's anything that's not clear. The first one, which is one of the basic ones, is the actual age interval. So this is referred to as x plus n. So the age interval from exact age x to exact age x plus n, such as if the age interval is 5 years, it's going to be exact age 40 to age 40 plus 5 to 45. The next column is the mortality. Now, this is the age-specific mortality rates that you covered in the last session. And this is the basis for the whole life table. And you see in these two graphs how the mortality will vary in a population. I've got the top graph is the linear scale and the bottom graph is the log scale. And the example we're using here is actually a high mortality country. And what you can see is, if you look closely, is that in the years 0 to 4, especially 0 to 1, there's high mortality. This is a country with high infant and high child mortality. After about age 5, you see the mortality decline to very low levels. And when you look at the linear scale, you can't really see very much of a difference until about age 45, 50, like kind of middle age, when then it starts to increase, and then it basically takes off from about 70 plus. The mortality rates then increase sharply. And if you look down at the log scale, you can see this much more clearly. You see the increase at the younger ages is magnified by the log scale, and then the kind of increasing rates at older age. You may come across either small NMX or large NMX. The difference between the two is that the small M refers to the mortality rates in the cohort population, and the large M refers to the observed rates in the population. And you don't need to really worry about that in this case, because we're going to make a basic assumption that the two are equal, that the mortality rates in the observed mortality rates in the population are going to be the same as the cohort rates. And that's kind of the basis of the period life table. Now, the next column is known as NQX. This is the conditional probability of dying in the interval x plus n, given survival to age x. So 5Q40 is the probability of a person who has survived to age 40, surviving through that interval to exact age 45. And if you look at the two graphs, you can see that they're very similar to the ones we saw previously, but they're not exactly the same. And this is refers back to this difference between risk and rate. So we have the mortality rates, and we have to transfer them into a probability. So they're similar, but they're not exactly the same. And this is really the key parameter that we see in the life table. Everything else is going to be directly derived from this. Is that clear so far? Any questions? Okay. Now, again, we're looking at this country with high mortality in the example, and this next column is LX, which is the number of survivors at exact age X. So if we see L40, that means the number of people who survived through to exact age 40. So it depends on the number that we've chosen to start the cohort. And that first entry for age 0 is often known as the radix. Now, in the end, when we finish the life table, LX must equal 0, i.e. there's no survivors, and this parameter can only decrease. So with a cohort, we've started off with the births, and it can only go down. And if you want to calculate the probability of survival to exact age X, then all you have to do is divide the survivors at age X by the number of people who started the cohort, the radix, and that gives you that probability of survival to exact age X. And again, we're looking at the graph, we see this high mortality example where there's a sharp drop in the cohort size in the first few years of life, and then it tails off, and then there's a sharp decline in older age. The next column that we use is NDX. Now this refers to the number of deaths in the interval X plus N. So if you see 5D40, that means the number of people who died between exact age 40 and exact age 45. Now this graph, as you can see, it does follow a similar pattern to the probability of dying at younger ages, but because it's dependent on the number of survivors, as the number of survivors decreases, even though the risk of death is going up, the probability of dying goes up, you actually see that the absolute number of deaths decreases because there are so few survivors in the cohort. So this looks something like in this graph here. A lot of deaths to begin with, it declines. You see an increase of death until about 70, and then it declines. Even though the probability has gone up, there are fewer survivors. So you see the number of deaths decline. Now, the next two columns are related to one another very directly. The N big LX and TX. Now, LX, this is known as the person years lived. So it's a function of the number of people who start the cohort and how many die in that interval. So the numbers who are left and how many years they're living on average. And there's another parameter which affects this, and that is when on average in the interval people die. So we have the number of survivors who start the interval, we have the number of deaths, but we also need to know when in the interval people die on average. So we're using sometimes quite large intervals, 5 years, 10 years, and we can't assume that everyone's going to die on average in the middle. Do you have any ideas about what might affect when in the interval people die? Does anyone want to have a guess? Okay, well, if you look at the graph in the picture, and you see this is the number, this is the LX and the being graphed. The shape of the mortality within the interval, that's the key element in defining when people are going to die in that interval. And it differs by the mortality rates in the population. So for example, if you've got high infant mortality, then children are going to die throughout that 0 to 1 age group, but they're going to be shifted more towards later infancy. Whereas in low infant mortality countries, children tend to die very early on in that interval, because the environmental conditions and the sanitation conditions and so on are better. So there's more of an emphasis on that really early period in the interval. So you'll see, for example, that if we look at when in the interval people die, and we look at the infants, the 0 to 1, if we look at a high mortality country, then there's going to be more deaths towards the middle of the interval and towards the end of the interval. And if we look at a low mortality country, then the babies who die on average. So that affects then the number of person years lived within the interval. Similarly, if we go to the older age groups, we would see the opposite. So we've got an age group where mortality is increasing, in some cases quite sharply. So the people who die, they're going to be exposed to higher mortality rates at the end of the age group rather than at the beginning of the age group, and that shifts the proportion of people who die towards the end. So then there's more person years lived in the interval. Is that clear to everyone? You can give me a thumbs up if it's clear. Is it not clear? Okay. All right, thank you. It's an important concept, and we're going to come back to this calculation in a little bit. So I just want to make sure that everyone understands it conceptually before we move on to the calculations. TX is basically the total person years lived above age X. So it's just a summation of LX from the bottom to the end of the age group from wherever you're starting. So T40 would refer to the number of person years lived in this life table above exact age 40. Now we try to show it graphically here, these different concepts. So we have the person years lived, this square under the curve. So all this area under the curve, the person years lived, whereas the T, the total person years lived above age X, in this case 65, that's that shaded area in the graph. So all of that area under the line, in this example, that would sum up to T65. And then that brings us to the last column in the life table, and that's the expectation of life at exact age X. Now, the most common use of this is the life expectancy at birth, and that is the number of years a person can expect to live in his or her life, prevailing mortality rates. And that's a key assumption. We're assuming that the mortality rates of today are going to last throughout that person, and that gives us the life expectancy. Of course, it doesn't mean that a child born today is going to live on average that life expectancy, because as Chloe mentioned earlier, we know that mortality does change. Now, the other thing about life expectancy is that we also want to use and need to have life expectancy at other ages, and that's also important. So we may want to know the life expectancy at age 40. So we want to know if someone survived to 40, what is their remaining expected years of life? This from the cumulative life years at age X, at TX that we saw before, and we divide it by the number of survivors at age X, which is the LX, which we've referred to before. And then that gives us the number of years left, the expected number of years left. Now, if you look at the example here, you see something interesting. You see that it's a similar pattern to LX, but unlike LX, you can actually see that this parameter can increase with age. This is something you sometimes see in higher mortality countries, where in effect, the life expectancy increases in the first few years of life. And this is generally due to high infant and child mortality rates. So once you've survived the certain critical periods of risks, mainly this childhood with many child diseases and risks of accidents and death, you are often stronger biologically. You've managed to to survive a difficult period, and in fact, your life expectancy at age 5 can be higher than your life expectancy at age 0. Sometimes people struggle to understand. But if you look at in the life table, issue seems to have arisen a lot with COVID, is that I'm sure we've all seen that people sometimes downplay COVID. Like, say, example, in Thailand, they say, well, life expectancy in Thailand is 70 and the average age of death from COVID is 75. So this is okay because, people, they've lived past what they should have lived, right? And that's obviously, apart from, the moral issues, it's a complete misunderstanding of what life expectancy means and what it is. Because, of course, those who survive to 70 may well have a life expectancy, being survivors, their life expectancy is quite a bit longer. They might have life expectancy of another 20, 25 years to age 70. So we also need to look, if we're going to do this analysis of the impact of COVID and life expectancy, it's not enough just to look at how has COVID affected life expectancy at birth. It may have had an effect. I know in the US there has been some effect at life expectancy at birth. But since we know COVID doesn't impact children and infants so greatly, we don't expect to see that really having an impact on child and infant mortality. But if we looked at life expectancy at age 60, we may see a massive impact. So people who want to look at the impact of COVID on the most affected population, that would be a metric that could be of interest and could be used. Are there any questions so far? Okay. So then we go to this NAX that we looked at earlier, and this is the average life lived in the interval by those dying in the age interval. So again, this problem is that the deaths are not linearly distributed within the age interval. Like, people don't die usually at the midpoint because mortality is not linearly distributed. To be the case. And actually, where mortality is not changing a lot, it's not a terrible assumption. If you want to be very precise, then you wouldn't just make this assumption, but it's not awful for quite a few of the age groups. But it is very off when we look at the youngest age group and the oldest age groups. So it's particularly tricky for the 0 to 1 and the 1 to 4. So we have to use a different method when we look at those age groups. So the way that we can get to this, there's a number of strategies we can use. One is that we can model the mortality function. So we kind of know what mortality patterns look like. So we can apply those and come up with a model of the mortality function, but this is quite complicated. And another alternative is to use values from a population. So if there's a similar population that's been observed and we know what these values are, then we can use those. So that's a good alternative to drawing the values from a similar population, whether this is already being observed. Or we can assume all die at the midpoint on an average. So when I was preparing for this presentation, I was looking online for something that could summarize this. But actually, the best summary I could find was from one of my old textbooks. So I've taken a photo and put it up here. And what you can see is that this 0 to 1 and 1 to 4, they're not, on the most part, there's not, the deaths aren't occurring at the midpoint, right? So you'd expect it to be half at the midpoint. But when you go to the older age groups, which are these 5-year age groups, you'd expect it to be an AX to be 2.5 in a 5-year age group if deaths are happening in the middle. And what you can see is like, it's not so terrible, right? I mean, you know, they're not far off 2.5 for the most part. So we can kind of go right here for our own purposes. We're not going to go into the modelling of mortality. I mean, we certainly can. If you're interested, we can do that in the next lesson to let us know. But I think for now we can leave that. We're not going to draw in values from another population, which is entirely legitimate. What we do is we're going to use a rule of thumb, and we're going to look at how this can be roughly estimated for purposes. Any questions so far? Okay, so what we've got here is an example of a life table, and this is what it looks like when we put it all together. So you can see at the top the different the notation, and then we can see this is an abridged table, these separated life table. Then all the way through we have the 5-year until the very end, which is also a bit of a different interval, has to be treated a bit differently. This is this last age group, the open-ended interval. All right, so now we're going to go back to the columns, and we're going to look at the calculations, which is what we're going to give you for the tutorial, for the assignment. So again, age speciality rate, just exactly what you covered last session. The deaths, and this is in the population. If you look at the cohort mortality in the life table, for the small m, the calculation is a bit different, but because we're going to use the population mortality rates that have been observed, so that's why it's a big M in this case, and it's the deaths of the people during the year, being the ages over the mid-year population, and we're going to assume that this is the same as the cohort life table. So we're going to assume big M is going to be equal to small m. Right, so now we have this issue. How do we go from the rate to the probability? And here we've got an equation which roughly comes up with the right answer. And all you have to do here is just plug in the numbers. Okay, so N is the width of the interval, the mortality rates in that interval, and then we cut NAX. Okay, so this is the one we were referring to earlier, which is the average years lived of the people who died in the interval. And what we will do here is it's okay to use, okay, so other than in the youngest age group. So this means that for the standard 5-year age groups, it's going to be 2.5. What do you think, though, this might be for the oldest age groups? Does anyone know why it actually doesn't matter for the 85 plus? What do you think the probability of dying is going to be for the oldest age group? The open-ended one, which closes the life table. What would be the probability of dying? You can write it in the chat. Do you remember that the basic assumption of the life table is higher, but the probability of dying in the open-ended age group to finish the age group, by the end of the life table, everyone dies. Which probability of dying has got to be? If everyone dies, it's going to be 1, right? So whatever the mortality rate, it doesn't matter. So we don't need to worry about calculating NQX for the last age group, because just by virtue of being the open-ended age group, everyone will die in that group. So that NQX for that one will be 1. But for the younger age group, we do have to calculate it a bit differently, and we will show you the rule of thumb that we're going to use for calculating this in the youngest age groups. We can't just do N/2 because it doesn't work, like we saw in that example that I showed before from real population. We can't use N/2, and also, as I mentioned earlier, in high mortality and low mortality settings, it's going to be quite different where people die on average in that age group. So here is the calculation, this rule of thumb that we use for the youngest age group, and this comes from observed data. So it's not going to be exactly true for every population, but it's good enough. So, as we said, the lower the levels of mortality, the more concentrated deaths are at the earlier ages of infancy. So to calculate in the first age group, 1A0, if mortality is above this rate of 0.107, these are the values that you use. If it's below 0.107, then there's a calculation that you use to calculate it as a function of that mortality. So if it's higher, you can just plug in these values. It doesn't change that much. If it's lower, then it gets more and more concentrated at the earlier ages, depending on what that level of mortality is. And you apply a similar equation based on the 1M0. So you only need really the infant mortality to be able to calculate this. And you come up with these values for NAX for those youngest age groups, for 0 to 1 and 1 to 4. Any questions so far? Okay. So then we come to this probability of surviving. So this one we didn't refer to earlier, but it's basically derived from QX. You either survive, which is P, or you die, which is Q. So MPX is just 1 minus NQX. And of course, if you add the two together, you're going to get 1. So it's either you survive or you die. But you see this one is going to be referred to in another one of the formulae. Okay, so here we are with LX. And if you recall, LX is the number of survivors at age X. And the way you calculate LX is that you take the previous interval, you divide times by the number of people who survived the previous interval, and that gives you your figure in the current interval. So say we wanted to know LX at age 40, how many survivors are there at exact age 40? We would take the number of people who started at age 35, times it by the probability of surviving that 5-year interval, and that would give us the survivors at age 40. Now, so in the open-ended interval, as we saw, Q is 1. This means the number of people dying has got to be the same as the number of people alive at the start. So the two are going to be equal. So the number of deaths in the last category equals the number of people surviving, because the probability of death is 1. Any questions? Is it all clear? Okay, so I know it's a lot of formulae and notation, but I think the concepts are not too complicated. If we come back to the number of person years lived between age X and X plus N. So everyone who dies in the interval, they're contributing a certain amount of years lived, and we need to take that into account, obviously. And that fraction that they contribute is this NAX years that they live, that they're contributing. So when we calculate the number of person years lived, we are making it a function of the width of the interval. So obviously the longer the interval, the more years lived there are. It's the number of the end of that interval, and it's the we want to include the contribution of those who died. Deaths by NAX, by the average years lived by people who died. Okay, so again, we go back to this NAX, and again, this differs according to the different age intervals and the assumptions that we've made. Now, when we come to the final age group, the open-ended one, it's got no defined length, so we can't do that. So we make an assumption here, and we calculate it as being the number of people who started that interval over the mortality rate in that interval, and that will give us the number on an estimate of the number of life years lived of the people in this age group. Now, it's not a great assumption. There's some other very complicated ways of calculating this a bit better, but there's no great solution to this open-ended interval because it is basically, in principle, it goes on to infinity, and it's different lengths for different cohorts. So ideally, we try to make this group as small as possible. So we don't want it to be too small that statistically it's going to be meaningless, but generally 85 plus is used as a good point at which to have the open-ended interval. Are there any questions so far? Okay, I'll move on to T. So this is just basically summing the life years from the age X, from whichever age you're interested in. So if it's from life, if you want from 0, you just sum up the entire life table, and then if you want from 40, you sum up from 40 to the end of the life table. So it's just a summation of the person years lived, the LX, the big LX. And again, from that, we get to life expectancy, the period life expectancy at age X. And this is the expected number of years lived, years of life remaining for a person alive at the beginning of interval X. And this is going to be calculated by the cumulative person years lived over the number of survivors at that age. So as we mentioned, this E0 is going to be the average number of years available to a newborn, which is the expectation of life at birth. And you would calculate that by summing the entire person years of the entire life table divided by the number of people who start the life table. Okay, so we'll move to the assignment, but before we go on to the assignment, is this all clear? Are all the calculations clear and the assumptions and the concept behind them clear? Is the notation clear as well? Because it's really important to understand conceptually these formulae, and also to have over the notation which is using. Otherwise, it can get extremely complicated and you can get lost. Okay, so thank you, Alison. Thanks for confirming. Okay, in which case I will hand over to Chloe, who will talk you through the assignment for next week. Thank you.
Thank you, Petra. So for this week's assignment, we would like you to calculate the life tables for Oceania region. We will provide you with the population estimates and the number of deaths for the periods 1950 to 55, and then we'll also give you the population estimates and death estimates for the most current period that we have data for, as it will be quite interesting for you to compare mortality estimates and life expectancy between these 2 points in time to see how they've changed. So I'll just share with you briefly the Excel that I'll be sharing with you later today. Hopefully you can see. So you'll see here that we've already pre-filled in all the information that you need to estimate a life table. So you have your deaths here and reported population. And so what we'd like you to do is to fill in the blanks, basically, using Excel functions to calculate each column of the life table. So using Excel functions and the equation from the slides. And we've also provided the solution, so you can check your answers against this to see if you're on the right path. And yeah, as usual, if you have any questions, you can let us know, or if you want to schedule tutorials, we could go through it together. I think that's all for today. Does anybody have any questions? Okay, I don't see any hands. Okay, well, I think that's all from me. Oh, thanks, Alison. Yep. Okay. Thank you very much, and have a good week, everyone. And please sorry,
just to
Petra.
jump in. Yeah, just to jump in. I think what we'll do next week is we're going to use these life tables to do some analysis of the life tables. So we'll use the ones which you've completed in the assignments to analyze the difference in some of the mortality. So while you're working through it, have a think about some of these differences in mortality and what they might and how we might analyze them, because we'll do that next week.
Thank you.
Okay.
Hi, Alison.
Hi, Chloe. Thank you.
Harry.
Thank you, Chloe.
Do you have any questions?
No, not yet, but I'm sure once I start doing my assignments, I'll reach out if I have any questions.
Okay, no problem.
Yeah, I still have other assignments to catch up on, but I'm looking forward to this one because it's Oceania, so it'll be interesting to see the difference between Palau and the rest of the countries.
Yeah, definitely. And then you can also use your own data to calculate your life tables.
Yeah. Thank you.
Okay, good. Thank you. Have a good week.
You too. Bye.
Bye.
Thank you.